Hello everyone, I'm very glad to do the presentation today. I'm Dr. Ying Xu from Tianjin University, China. Today, I'd like to talk about the progressive collapse-resisting performance of single-layer latticed shells with prefabricated joint systems. The outlines of my presentation are as follows. The first part is a brief introduction to the research background. Progressive collapse accidents of large-span spatial structures seriously threaten public safety, since they usually serve as public infrastructure and emergency shelters. It's found that most collapse accidents are caused by design flaws, improper construction, or extreme weather, such as heavy snow exposure. To avoid similar accidents, the PCRC is gradually becoming an essential requirement in the design of spatial structures. For single-layer latticed shells, the redundancy is relatively lower than that of other spatial structures. The progressive collapse mechanism of single-layer latticed shells has become a hot issue in the last decade. However, previous studies on the PCRC of latticed shells are mainly focused on welded joint latticed shells instead of prefabricated latticed shells. For prefabricated latticed shells, the insufficient joint stiffness may lead to the local buckling of joints and the further progressive collapse of structure. The representative case is the collapse accident happened in Inner Mongolia in 2005. In this study, a progressive collapse test was conducted to evaluate the influence of joint stiffness on the PCRC of single-layer prefabricated lattice shells. The test model is a three-way cylindrical lattice shell with a span of 4.5 meters, and the raised-to-span ratio is a quarter. All members are rectangular steel tubes, and the Type 2 assembled half joint is adopted as the joint system. The latticed shell model was installed on the support frame through the fixed hinge supports. The test was divided into two stages, the static loading stage and the progressive collapse stage. In addition, a novel instantaneous failure device is introduced to simulate the breaking of joint in the progressive collapse test. The data acquisition system includes a 3D laser scanner for coordinate measurements of joints, and the multi-channel dynamic strain collecting network, and a non-contact displacement acquisition system, which is composed of the high-speed camera system and the observation target arranged on the nodes. Then the FE model was also established in IASS. In FE analysis, the joints were considered to be semi-rigid and simulated by the combined spring model. The progressive collapse simulation was carried out by the LS-DYNA Explicit Dynamic Analysis Program. In this study, an effective method is proposed to evaluate the PCRC of lattice shells based on the critical progressive collapse load, which is CPCL in short. Explicit dynamic analysis was carried out successively to obtain a CPCL corresponding to different initial failure joints. As shown in the figure, G3B with the lowest CPCL is selected as the initial failure joint in the test. During the static loading test, there were 5 loading grades in total. The full span of the dead load plus half span of the live load was applied as concentrated loads on the joints. The test results show that the structural responses were approximately linear with the static loads, and the shell performed elastically in the static test. After loading level 3, the test model exhibited obvious antisymmetric deformation. Then the progressive collapse test was carried out at the last loading grade. In the first stage, G3B and the adjacent diagonal members were failed by triggering the instantaneous failure device. Then the joints in zone 2 started to move downward. In stage 3, the local instability of the side span was observed, and the joints in zone 4 experienced the upward displacement until they finally reached the highest point in stage 4. In stage 5, with the further transmission of loads, the joints in zone 4 started to move downward, and the joints in zone 2 had a continuous downward movement until they finally touched the floor. The test video and the displacement nephogram of the FE model are compared, it's found that the progressive collapse of the test model showed brittle features. Most of the joints experienced a connection failure during the collapse. It's also found that the simulation's results fit very well with the test phenomena. A clear load transfer path can be determined based on the displacement and strain responses. The process of member failure shows obvious sequentiality and dynamic effect characteristic. Subsequently, a parametric analysis was carried out to evaluate influence of joint stiffness on the PCRC of single-layer cylindrical latticed shells. In parametric analysis, the joint system was assumed to be rigid and semi-rigid respectively. Both the type 1 and type 2 assembled half joints were considered. The left figures show the CPCL corresponding to different initial failure joints in the shell models. It's indicated that the PCRC of the rigid jointed shell is 22% higher than those of the semi-rigid jointed shells. The right figure shows the relationship between the loading level and the maximum vertical displacement of the shell after removing the initial failure joint. It's found that the performance of the type 1H joint is better than those of the other joints from the perspective of ductility. This page shows the displacement time histories of the three models when after removing the initial failure joint. The snap-through collapse mode is more obvious in the latticed shell with type 1H joints, which manifests with a higher positive displacement. This page shows the development of energy during progressive collapse. After the initial failure of joint, the gravitational potential energy and external work are converted into kinetic energy and strain energy. In the later stage of collapse, the kinetic energy will be further converted into strain energy and will gradually decline to zero. The shell model with better PCRC is able to absorb greater strain energy during progressive collapse. As shown in the figure, the total strain energy of the rigid jointed lattice shell during progressive collapse is larger than those of the prefabricated lattice shells. This observation further explains why the PCRC of the rigid jointed shell is higher than those of the semi-rigid jointed shells. Based on the above studies, the conclusions are summarized as follows. Okay, that's all of my presentation, and thank you for listening.